Hello everyone, and today I'm going to do something to do with calculus, and I'm going to do something which just proves this arbitrary quote which I'm going to say right now. Integration is an art. It absolutely is an art, okay? So differentiation is just technique, but when you integrate something, you have to think really outside of the box and even do the most obvious things which you would never think about. So here we have some reciprocal trig functions, which can be distinguished from inverse trig integrals, which is integrating stuff like the inverse function of tan. But we're not doing that. We're just gonna stick to this. So cotangent, secant, and cosecant. That's essentially what we mean when I say that. Or that's what I mean. I've never heard this term used before. But anyway, let's press on. And the first integral we have here might seem like it would be hard, or the hardest out of the three, because normally tangent is the most complicated regular trig function, but it actually works opposite. It's really funny. So again, there's a sense of duality in trig functions. Anyway, let's press on. And I just want to remind you that cotangent just means tangent to the power of -1, a reciprocal version, so that is this thing, the inverse of that. So essentially we're integrating cosine of x divided by sine of x. And what is that? How are we going to solve it? Let's think out of the box. So what is essentially the cosine function in terms of the sine function? It is the derivative. So what we can do here is we can do a little trick, and we can rewrite this as a substitution. So remember we covered u substitution. I know it was a while ago, but we're going to quickly recall that fact. And if we're going to say that this is equal to some function u, an inner function u, then cosine, what would cosine be? It would be, well, let's check it out. If we differentiate, sine of x, what do we get? We get cosine of x. So it's just as simple as that. And now in terms of u, I'm going to say, so du over dx, that is equal to cosine of x. So then du would be cosine of x dx. So then we can just make this quick substitution and end up with u in the denominator, du in the numerator. And it couldn't be more easy. It's just more aesthetic this way. And essentially, if you remember the 1 over whatever, that always integrates back to the natural logarithm. That's just one of the stuff I covered in the first videos in this playlist. And so if I'm now to rewrite it, not rewrite it, sorry, just actually solve it, that would be natural logarithm. And I'm going to use, by the convention, I'm going to use the modulus symbol. You really don't have to, it's just, I mean, it's quite obvious we're not going to have a negative number in it. Okay, whatever. And constant of integration, never forget about that, because that is essentially what we end up with. And I'm just substituting back for u. Okay, so now let's do number 2. And number 2 is very special, because that's where we end up with the actual fun bits. And as you can see, I'm very good at ripping pages off my notebook. Anyway, what we're going to do here is we're going to do a very cheeky little method, which is essentially like rationalizing an expression. It's not really rationalizing, but timesing both the denominator and the numerator by the same expression in order to get it simplified or kind of treated in a way. So what we're going to do is we're going to represent this as integral of secant of x divide by 1, yep. Integration by each, again, a very silly thing. If you're dividing by 1, but anyway. And we're going to times both sides by something that's very similar to the derivative of secant function, but isn't quite it. So and that's really special because we're gonna get a mind-blowing result. And I highly recommend you try to solve it in a different way because it's just not going to work. This is the only method I've come across which actually works. So we get the secant of x squared because we're multiplying by that. And by the rules of FOIL multiplication, also get here plus tan of x secant of x, all that divided by basically this. This is just 1 times that thing. So, and this is very interesting because what we got right now, and there's an integral here. We have here an expression which is broken into 2 parts, so we can easily work out its derivative separately. And this is the derivative of this, and this expression over here is also the derivative of that way around. So we have corresponding derivatives here. So tan differentiates to secant squared, secant differentiates to tan times secant of x. So yeah, we just know that this is a derivative. So we can kind of use our natural instincts and say that this is the integral of du over u, or essentially 1 over u du, and we already know that that is going to be ln of u with a positive argument here. So that is the natural logarithm of secant of x plus tan of x plus c. Okay, so now let's do the last one. Just going to check it. Yeah, okay, so we're going to do something that's virtually parallel to what we did right now. Okay, so we're going to start off with the cosecant of x over 1 times it by something that's very similar to the derivative of cosecant but isn't quite the same thing from both sides, and that is cosecant plus cotangent. Which is, again, it links back to the derivative of cosecant being minus cotangent x times cosecant of x. Just like here, the expression we got here is related to the derivative of the secant function, which is secant times the tangent. So here we were going to have the same thing, and next step we're gonna integrate, but first you have to simplify it, and we'll have, as you've noticed, the same spiel, the same thing. You get the gist. It just cosecant squared of x plus cotangent times cosecant of x. And I think you'd have noticed by now this is virtually the same thing as what we did before, just a parallel. So just like I mentioned in that other video, a very basic video about finding the integrals of trig functions. Okay, so now we know that here we can have this as our new denominator, plus cotangent of x, and this over here we can differentiate it to get something not quite this, the minus version, the negative version of this. Again, made the same stupid mistake. This differentiates to this, whereas the cosecant differentiates to this expression over here. So then, yeah, we can just write it as the integral of if this can get a substitution u, we can say that perhaps we can see what u differentiates to. So du over dx is going to be cosecant squared x minus cotangent x times cosecant x, and then it's just a minus instead of a plus, so we just do minus du, which is in turn so that is in turn the integral of minus reciprocal of u du, and that is, by now I should master it, it is natural logarithm of u minus natural logarithm, because you have minus here, and that is minus natural logarithm of what we started with is, what is u? U is cosecant x plus cotangent x, and that's it, and we don't have to do anything else. But yes, we have to do the constant of integration. So I hope you found it useful, and I'll definitely make more videos about high-level integration, because otherwise there's no point in just showing you the basics unless you actually get hero with it. You know, that's the name of the playlist, 0 to hero. So I'll see you in the next video. It was lovely making this video, and credit to my friend who gave me this idea. And so yeah, hope you enjoyed it. I hope it was useful. This stuff is quite advanced, I think, for integration, and yeah, I'll see you in the next video, which will probably be another integration video. So yeah, see ya.